Hey there. Okay, so today I want to talk about carbon nanotube structure and mechanical properties. So carbon nanotubes are basically rolled up sheets of graphene. They're allotropes of carbon. They have a cylindrical nanostructure. Most of them have end caps on them. Nanotubes have been constructed with a length-to-diameter ratio of up to 132 million to 1, which is significantly larger than for any other material. And this makes them kind of ideal as nanowires, which we'll talk about in a later lecture. Even regular nanotubes, though, have diameters of about 2 nanometers and lengths of 100 micrometers, so they're effectively nanowires. Now, the first thing I want to talk about is the different types of nanotubes and how you roll them up, and what's called a chiral vector. Okay, so it's kind of easy to imagine a nanotube as a rolled up sheet of graphene. And then there's 3 different ways that you can roll up the sheet, leading to 3 different types of structures. The names of the structures are armchair structure nanotubes, zigzag structure nanotubes, and chiral structure nanotubes. Okay, and of course most nanotubes are closed at both ends. And so the cartoons in this image kind of show you what a zigzag structure nanotube roll-up would look like, an armchair nanotube roll-up would look like, and then a chiral nanotube would look like. Now, the different structures have different electrical properties. The armchair structure is a metallic nanotube, so that acts as a nanowire. The zigzag and chiral structures are semiconducting. And in the semiconducting tubes, you can change the band gap by changing the diameter of the nanotube. The energy gap actually increases as the nanotube diameter decreases. And here's some cartoons of what the armchair, zigzag, and chiral nanotubes look like in sort of a top-down view. So let me tell you a little bit more about the chiral vector. The chiral vector often has a notation of n, m, like a coordinate set. And it describes the nanotube geometry. And n and m are integers, and they're integers of the vectoral equation n times a1 plus m times a2. Okay, so if you imagine that the nanotube is unraveled into a planar sheet, then you would figure out what kind of structure you have by doing the following. Draw 2 lines along the tube axis where the separation takes place. In other words, if you were to have a rolled up nanotube, you would make a cut down the nanotube. Okay. If you have the cut and then you unroll it, you would get the 2 blue lines that are shown here in this little cartoon. All right. And now what you do is you would match those ends together into a cylinder to get the nanotube that you started with. Now the red vector, the chiral vector, is indicated here, and it's in red. It goes across from point A to point B. Now, if you find any point on one of the blue lines that intersects one of the carbon atoms, we'll call that point A here, there's a carbon atom. And then what you do is you draw what's called the armchair line, and that's the thin yellow line that's labeled armchair here in that. And what it does is it travels across the hexagon and separates the hexagons into 2 equal halves, okay? And it also goes along one of the lines of the hexagon, so you can see the armchair line there. Now that you have your armchair line drawn, find a point along the other tube axis that intersects a carbon atom. And you can see that here, that's B. And then what would happen is if you rolled the tube up, that would be the same atom, okay? Now, the chiral angle is not shown on this cartoon, but it's formed between the vector R, which is shown in red here, and the armchair line, which is that thin yellow line. So that would be the angle, theta, okay? If R lies along the armchair line, then theta is equal to 0, and of course it's an armchair nanotube. If theta is 30 degrees, then the tube is a zigzag nanotube. Otherwise, it's going to be between 0 and 30 degrees, and it's a chiral nanotube. The vector A1 lies along the zigzag line, so you can see what a zigzag nanotube would look like, and that's a 30-degree angle there, okay? The other vector has a different magnitude than A1, but its direction is a reflection of A1 over the armchair line. And when you add those 2 together, you get your chiral vector R. Now the values of N and M determine the chirality or the twist of the nanotube. If M equals 0, then the nanotubes are zigzag nanotubes, and if N equals M, then they're armchair nanotubes, and if they're anything else, they're chiral nanotubes. Once you have the chiral vector N comma N, M, then you can get the diameter of your carbon nanotube according to this formula, 0.0783 nanometers times the square root of N squared plus M squared plus N times N. Okay? And that comes from just the geometry of the system. And you can also calculate the chiral angle theta from the vector, NM. The cosine of theta would be equal to 2 times N plus M over 2 times the square root of N squared plus NM plus M squared. Okay, so all of that comes from the geometry of this situation. Now, the chirality of your nanotube would in turn affect the conductance of the nanotube, its density, its lattice structure, and a lot of other properties. SWNT stands for single-walled nanotube, and that's considered metallic if the value N minus M is divisible by 3. Otherwise, you've got yourself a semiconducting nanotube. Consequently, when the tubes are formed with random values of N and M, we would expect that 2/3 of the nanotubes would be semiconducting and the other third would be metallic, and that happens to be the case. All right. Now, nanotubes are have exceptionally high tensile strengths and ultimate strengths. So when we're talking about that, first it might be helpful for those of you that might not have had this material to see some definitions from material science of stress and strain and elasticity. Okay, so here we go. Let's assume that you've got a rod or a fiber or something, and you're applying a tensile stress to that. Now what that means is that you're pulling it so that the force is along the axis, the long axis of your fiber or rod. And those kinds of forces tend to stretch your object. This is the kind of force that would happen with a cable, for example, that was in tension, as shown here. Now, the change in length of the stretch object that would result from a given tensile force depends not only on the force that you apply, how much force, but also on the length of your cable and on the cross-sectional area of the cable and on the material from which the cable is made. For example, you get much more stretchiness out of an aluminum cable than you would maybe from some steels. The material factor is called the Young's modulus, and what that does is normalize out the length and the cross-sectional area. Okay, so it's a material property only. This material property has been measured for a whole bunch of materials. Now, the factors that we use to help calculate this stuff is the stress. And the stress is equal to the force that you apply in tension divided by the cross-sectional area of the material. So it attempts to get rid of the sort of geometry of the situation and only consider how fat it is. And you can imagine that if you have a fatter cable, of course, it can take a lot more force on it. Okay, so that's why you normalize that out and just consider the stress. Most times in material science, the stress is symbolized with the Greek letter sigma. Now, you're also going to have some kind of change in length as you stretch your cable out. Now, to normalize that for the length of the cable and not consider the length of the cable, so for example, for the same force, if you had a much longer cable, you would expect a different change in length for that. But to normalize that out, we define what's called the strain. And the strain is the change in length of the material, delta L, divided by the initial length of the material, L. And lots of times in material science, we use the Greek letter epsilon to symbolize the strain. And then the Young's modulus of the material, which is often symbolized by a capital E, Young's also elastic modulus is another sort of interchangeable way to put it. That's just supposed to consider the material properties. And that is going to be the stress divided by the strain, or sigma over epsilon. So when you plot this out, this is the modulus of elasticity, and before you begin to permanently deform the material, you get a linear relationship between your stress and your strain. And this is basically Hooke's law, okay? Physics majors should be familiar with Hooke's law at this point, that if you have a spring with a spring constant K, then F is equal to K times delta X, where delta X is the stretching of the spring. Well, if you divide that out so that it's not the force on the left-hand side of that equation, F is equal to Kx, but instead the force over the area, right, then you end up with sigma is equal to E times epsilon, which is sort of Hooke's law for materials, okay? Now this elastic modulus, or Young's modulus, E, is shown here in this table for a whole bunch of different materials. Okay, so you have your cast iron, 100 times 10 to the 9 pascals, brass, also 100 times 10 to the 9, aluminum, 70 times 10 to the 9. So you get a range of values there. And the Young's modulus for carbon nanotubes is roughly a factor of 10 times larger than the Young's modulus of steel. So it's a pretty impressive value if you think about it. The values range from 1.28 to 1.8 terapascals, and steels is about 0.2 terapascals for some steels, for different steels. There's a lot of different alloys, by the way, that make up steel, so the values for steel can go over a range, but carbon nanotubes greatly exceed that for steel. Now, if the stress that you apply in tension is too great, then the object is going to fracture or break. And this gives you the ultimate or tensile strength in the material under tensile stress. And the compressional stress and shear stress have also been measured. We're not going to talk about those today, but they've been measured. Now, what you can do in material science is plot what's called a stress-strain curve. And you're plotting the engineering stress versus the engineering strain. And you do that until the material breaks. Okay? The tensile strength is defined as the maximum stress or the maximum force per unit area on that stress-strain curve. Okay, so let me go over this curve here. This is what you would get out of a tensile strength tester like we have here in Garwood Hall on the second floor. In the linear part of the curve, that's where you've got your elastic modulus. Okay, so it responds, and then if you were to take that stress away, it would go back to the 0 point. Here, when it starts to bend, that's when you get plastic deformation in the material. In other words, you're starting to thin that wire out a little bit, and then eventually it starts to neck and then break off. So the maximum on that curve is your tensile strength. Now here's a table with some ultimate or tensile strengths of various materials. And this is where you're at when you break. Now your high strength steel alloys have tensile strengths of about 2 billion pascals, which is very impressive. But the tensile strength of carbon nanotubes, the single-walled ones, has been measured to be about 45 billion pascals. So they're much stronger than your steels. Now, usually materials that have high values of Young moduli are stiff materials. You might think of a ceramic or a glass material that doesn't stretch much as having a very stiff material that fractures and doesn't stretch out. But now nanotubes, okay? And that's because they're so thin. So, for example, there's a formula here to show the degree of bending of a nanotube. So here, D is the deflection of the nanotube that would happen in the lateral direction. F is the applied force to the nanotube to get it to bend in the sort of transverse direction. L is the length of the nanotube here. E is, of course, the elastic or Young's modulus in the material. And I is the areal moment of inertia, which is defined as pi times r naught to the fourth divided by r I to the fourth divided by 4. Okay? So pi times r naught to the fourth minus ri to the fourth divided by 4. That's your areal moment of inertia, where r naught stands for your outer radius and ri stands for the inner radius of your nanotube. So your formula D gives you the deflection, FL cubed over 3EI. So they're actually very flexible in addition to being very strong, which makes them, really particularly strange materials in material science. There was a study done in 2006 where they actually fired sort of little micro-scale bullets at nanotubes, or nanoscale bullets at nanotubes. So they fired them at the nanotube to the side with high speeds, and then they saw how the nanotubes sort of performed in response to these little nanoscale bullets. So their bullets were these little tiny pieces of diamond that they ranged in speed from 100 to 1500 meters per second. Just to give you a sense of perspective, the bullets that come out of regular guns travel up to, say, 1400 meters per second. So these are going at the same speeds as bullets. And the nanotubes actually performed very well. They can buckle. but not break, and then they can be straightened back out without permanent damage to the nanotubes. Usually defects in ceramic materials are the sites of breakage in the materials, but nanotubes have very few defects, and also the hybridization of the carbon bonds change as the bonds are sheared so they can bend without breaking. So these are all reasons that nanotubes perform so well with these little nanoscale bullets. And of course, it wasn't long, not long at all, before people started capitalizing on this and making body armor out of it. And if you want to see the armor actually shot with these bullets in a video, you can go to the link here and click on that, and you can watch that guy just fire away at this carbon nanotube body armor, which is for sale for the low, low price of $130 to $140 per panel. Okay, nanotubes have also shown to be good additives to composite materials. A composite material, of course, is a material that's a blend of different material types. What nanotubes do is they can really increase the strength while decreasing the weight. Since they're made out of carbon, they're just not super heavy like a metal would be. And so you can get body armor that's got, say, the same strength to it, but not be as heavy for the person wearing the armor to carry. There's an equation called the Kelly-Tyson equation that describes how the tensile strength of materials vary as you change the volume fraction. And here it plots the tensile strength of steel and how it would increase based upon the volume fraction of carbon nanotubes that you would add to it. So this is a sort of theoretical prediction. And nanotubes have been shown to form good strong bonds with iron, which is a main constituent of steel. So it might make a nice additive. And of course, these have also found commercial applications already. So here you see a picture of a boat made by Zyvex Marine in Seattle, Washington. And they announced the launch of this boat here, the long-range vessel, that's designed to combat piracy. And it features fuel efficiency, and that's because, of course, of the light weight of the carbon nanofibers. So it's very efficient on fuel because it's not very heavy, and also it helps stabilize in rough seas. It's got a fast sprint speed of 40 knots, also because of the light weight of the carbon material, and a range of more than 1,500 nautical miles because it's very fuel efficient. It's made of Aerovex, which is a carbon fiber nano composite system, a carbon fiber composite enhanced with nanotubes. And it reduces the weight, but also is very, very strong, which you would hope for in a boat. There's also lots of applications in sports due to the high strength and lightweight material. Carbon nanotubes are being used in all kinds of sporting equipment, including golf shafts, which are shown above, shoe soles, archery arrows, baseball bats, bicycles, etc. In fact, in 2005, in the Tour de France, one of the bicycles there featured, it was the first time in 2005. I'm not sure how many times it's happened since then, but the frame of this BMC bike is called the Pro Machine. It weighs less than a kilogram, and the Phonak cycling team used this bike in the Tour de France in 2005. And to quote a news article about it, to create the frame, BMC used a composite technology developed by U.S. sports equipment specialist Easton, and the company's enhanced resin system embeds carbon fiber in a resin matrix that's reinforced with carbon nanotubes. So whenever you want to increase the strength of a material while not increasing the weight over much, then carbon nanotubes and carbon fibers are a really good choice. Now, why are they so strong? Like, what's the physics behind this? Okay, well, as we discussed in previous videos, the carbon in the nanotubes, they form these covalent bonds, and these covalent bonds, the covalent bonds in carbon, are hybridized bonds, so it's sp2 and sp3 hybridization. Now, covalent bonds are directional bonds, okay? This is different from a metallic or the electron C bond, okay? So in a metal, which is pictured here in the cartoon above, you have these metal iron cores kind of surrounded by the C. And as you can imagine, there's no real preferred direction for these bonds, okay? So they're spherically symmetric, right? Now, In a metal, what happens is, because these bonds are spherically symmetric, you can get slippage, and one atom can move into the next lattice site, okay? So you're not really breaking the bond so much as shifting one atom into the position, and it can do that easily. But with a very directional bond, like a covalent bond, you can't do that, right? You have a carbon bonded to another carbon over here, and that bond is very, very directional, all right? So you can't have this carbon just slip into here or slip into there, because this bond has a very strong directional component to it. All right. So in a metal, when you pull on a metal, it's ductile. It can be pulled, drawn into a wire, and the reason for that is those metal ion cores can move around and slip from one spot to another, and that doesn't happen in a carbon nanotube or in a carbon material. So that makes the bonds very strong. You can't pull it apart, draw it into a wire like you can in metal, thin it out, because of that reason. Now you might say to yourself, well, there's probably a lot of materials that have directional bonds, and they aren't as strong as nanotubes, so what's up with that? And you'd be right. So ceramics, for example, they have very strong directional bonds, and it's not so easy, for example, in a ceramic material which alternates a positive and a negative ion right in the structure. It's not easy for a positive ion to slip into a negative ion spot. So the slippage that occurs in metallic bonding doesn't occur for ceramics. But ceramic materials break at much lower tensile stresses than your carbon nanotube does. So what's up with that? Well, the tensile strength is much lower for ceramics than what you would predict from having to break a bond. So when you talk about breaking a ceramic, pulling it under tensile stress and having it fracture that way, you might think, well, what I'd have to do to get that to happen is to break every single bond along that cross section, but that's not really what happens. What happens in a ceramic material is that you've got defects in the material, little micro voids, internal pores, inclusions, maybe a scratch on the surface, something like that. And then what happens is the fracture starts there, starts at that defect, and propagates outward. That crack propagates outward, and you get brittle fracture. So there are people that do analysis on materials when they break, and they try and figure out what the origin of the fracture site was, and so on and so forth. That's pictured here in this image, where you see a fracture origin and it propagating out from there. Now, the nanotubes are strong, okay, basically because they're nanoscale materials and not these bulk materials, so you don't get those defects, those types of defect forming like you do in a bulk material. You don't have pores and surface scratches and micro voids in a nanotube the way you would, say, in a ceramic rod, okay? So those defects don't form, and so in order to break the nanotube, you really do have to break all those carbon-carbon bonds, and those carbon-carbon bonds are strong, okay? And so it takes a lot of energy to do that. Now, if you have, for example, instead of a single-walled nanotube, if you have a multi-walled nanotube, which is kind of like a nanotube nested within a larger nanotube and so on and so forth, then it's easier to pull it apart and break it. You can imagine the nanotubes kind of slipping over one another and pulling apart that way, kind of like a Russian nesting doll pulling it apart or something like that, okay? And if you made a fiber out of a bunch of nanotubes, then of course you could get defects in the fiber, all right? And it's been shown that the fibers, while they are quite strong, and the multi-walled nanotubes, while they are quite strong, are not as strong as your single-walled nanotubes in terms of tensile strength. So there you have it, all right? You got to have defects in order to break something, and in a little tiny nanotube like that, a nanoscale material, there's just not those defects that are present in a bulk material, and so you've got a large tensile strength. Okay? Hopefully that makes sense, and I'll see you in the next lecture.